2 weeks of seminars, and I'd like to again thank Professor Sigmund for the presence here and this nice mini course. I'm sure that we are all enjoying it very much. This afternoon, we are going to have only one talk. That's going to be at 1:30, and that's by Professor Fernanda de Mello, right, Sherry? So we have a little bit more time for lunch today. And I understand Jair is planning something for us tonight, but we are going to make announcements at a certain point. I don't want to put him on the spot right now. So that's basically the announcements I have, and it's my pleasure to introduce Professor Sigmund.
Introduce me slowly.
Yes, okay, take your time.
Thank you.
By now, we are all used to all difficulties we have with these things. So. Mais uma coisa que tem que botar, gente?
So I apologize for this delay. Excuse me. But I think now I've got it. So thanks very much again for introducing me. And I would like to say that last time I tried to stress that there are many different approaches to evolutionary game dynamics. There is a replicator equation, which I've written down again, and Martin Novak must have given you the impression that about everything that happens under the sun is governed by this replicator equation. But I would like to stress that it is not unique in any sense, that it is just a representative of a large, particularly versatile representative of a large family of equations. And it is interesting to study the whole family of imitation dynamics, for instance, where these xi are the frequencies of different strategies, and fij is the probability of switching from strategy G to strategy I, for instance. A case where this rate fij, this probability for switching, depends only on the payoff of the model strategy or depends only on the difference between the payoffs leads to a modification of the replicator dynamics where f would be any monotonically increasing function, for instance, and in particular if f is linear, we would be back to the replicator equation again. And I've also mentioned the best reply dynamics where at every moment the players are switching with a certain rate to whatever is currently the best strategy to given the composition of the population. So many of these dynamics are of the type xi dot is equal to xi times something, a per capita growth rate. And of course, since this is describing the evolution of frequencies, the sum of this xi dot must remain equal to 0, so that one stays on the unique simplex Sn. This means that if a strategy is missing, if xi is equal to 0, then xi dot is also equal to 0. It is not going to be introduced. This class of strategies, the boundary phases of the unit simplex remain invariant. And this creates, the boundary phases are invariant, and this creates a possibility for robust or structurally stable limit cycles, heteroclinic cycles. I've given an example with a rock, scissors, paper game. I would like to stress that there are many more complicated examples. for instance, here, if you have 4 different strategies, A, B, C, and D, you have 2 heteroclinic cycles. One is a cycle A, B, D, and back to A. And another one would be A, B, C, D, A. And if you start in the interior, it can be a very tricky question, and in fact it is not solved yet in full generality, to decide which one of these cycles is eventually going to win, which one is attracting the orbits from the interior or so. A particularly important class of this game dynamics is payoff monotonic, which means that the rate of growth of strategy I is larger than the rate of growth of strategy J, if and only if the payoff for strategy I is larger than the payoff of strategy G. And in this case, the Folk's theorem, you may remember this relating the dynamical properties of this equation with Nash equilibria holds again. So for instance, strict Nash equilibria are attractors for this dynamics, and so on. But as I mentioned, also the best reply dynamics would be different. In the best reply dynamics, a strategy which is missing originally can be introduced if it turns out to be the best reply to the current dynamics. So in the best reply dynamics, the boundary will not be invariant in general. If you start here on the boundary, the flow points inwards toward this strategy, if this is the best strategy. So this type of transmission or this type of mechanism governing the dynamics demands players which are more rational in some sense. They are not just imitating what is around in the population. They should be able to guess for the strategy that is currently the best option to them. And so this means that the players in some sense are more rational. I have also mentioned the last time that in evolutionary game dynamics, in contrast to classical game dynamics, the players are in general not assumed to be rational. Well, there are many different degrees of rationality, of course, but here in this best reply dynamics, there are some demands about the cognitive capacities of these players. But what is interesting is that even if in general in game dynamics one does not ask much about the rational capacities of the players, the outcome frequently is the same as that predicted by classical game theory, where one assumes that the players are rational. An instance of this would be the elimination of dominated strategies. What does this mean? A given strategy Y is said to be strictly dominated if there exists another strategy, which can be possibly a mixed strategy, with the property that whatever is the state in the population, whatever is the X, the payoff for a player using strategy Y, this would be the right-hand expression, is larger than the payoff for a player using strategy I. So in that case, one would assume that rational players would never use this strategy I, because it is never better than using this mixed strategy Y. Therefore, one would assume that this strategy can get eliminated. And this is a procedure actually that can be repeated several times in many situations. Consider, for instance, the example of this payoff matrix. You see immediately that the second strategy is dominated by the first strategy, because 0 is smaller than 5, 0 is smaller than 2, 4 is smaller than 7. So whatever the other player is doing, it is better to use strategy 1 than to use strategy 2. Now, since 2 is dominated, you can forget it and eliminate in your mind this second row, and also, of course, the second column in this payoff matrix. So you are left with a 2 by 2 matrix, 5, 7, 1, 5. And in this case, for this 2 by 2 matrix, the bottom row, the bottom strategy, is dominated by the top row, because 1 is smaller than 5 and 5 is smaller than 7. So you can go one step farther and say a rational player is never going to use strategy 3, for instance. So after having eliminated strategy 2, you can also eliminate strategy G, and you remain with one strategy, so strategy 1, which is obviously the solution in some sense for this game, if it is played among rational players. So interesting thing is that even if you do not assume rational players, even if you assume that these are bacteria, for instance, playing this, and if they are following, if the population dynamics is given by this variant of the replicator dynamics, then it turns out that iteratively dominated strategies will be eliminated in the long run for the population, from the population. The frequencies of these iteratively dominated strategies will converge to 0, provided that this growth function here is a convex function of the payoff. This has been shown by Hofbauer and Weibull, who also showed that if this function f is not convex, then there always exist counterexamples. There always exist games where iteratively dominated strategies will not get eliminated. So this is an interesting aspect, that in some situations the population of absolutely irrational actors just following some imitation or replication mechanism will hit upon the same solution to the game as two players which are completely rational and know that the other guy is also rational. I have so far not spoken about what is possibly the main and certainly the first concept in evolutionary game dynamics, which is the concept of an evolutionarily stable strategy. This was what Maynard Smith introduced some 30 years ago into this theory. And I want to turn now to this. And in order to do this, I want to discuss mixed strategies. So far, we have assumed that the players are using only some pure strategies, the corners of the simplex: rock, scissors, paper, or hawk and dove. Now we shall assume that a given type, a given phenotype of player can also use a mixed strategy, which consists on, for instance, if we are looking in the hawk-dove game or the chicken game, yes, we can consider not only a type of animal that plays hawk, the hawk strategy, which is a pure strategy saying you should always escalate. But we could consider a second type playing the dove strategy. Pure strategy says never to escalate. And then we could also consider how does a population, an individual fare if it plays a mixed strategy and escalates only with a certain probability, say of 50%, of 30%, or whatever. So in that case, we have three different types. E1 would be the pure type hawk, E2 would be the pure type dove, and E3 would be using this mixed strategy. So one individual who with a certain probability is going to escalate and with a certain probability is going to run away. In this case, for instance, we find that the replicator dynamics yields a line of fixed points. All these are fixed points of the replicator dynamics. And whenever you start, you converge toward this line of fixed points. And on this line of fixed points, there will be only neutral drift. So more generally, what happens if you introduce mixed strategies? This means that you have a game with some pure strategies. For instance, here 3 pure strategies, which would consider this would be a pure strategy, this would be a pure strategy, this would be a pure strategies. And 4 types, for instance, of players, of animals in a population, for instance. One type is playing the mixed strategy P1. The other type is playing mixed strategy P2. The third type mixed strategy P3. And the fourth type P4. And we can now compute what happens with the dynamics. So we can compute, first of all, the payoff for an individual using the mixed strategy Pi against an individual using the mixed strategy Pg. This is given by Uig. And we can consider the state of the population, x1 to xn, now capital N instead of small n. Yes, small n means here the number of different pure strategies, and capital N means the number of different types in the population. And xi would be the frequency of in the population using strategy pi. One can easily compute the mean strategy in the population because xi is the frequency of those who are using the strategy pi. And then one can write down the replicator dynamics, and it turns out that this is just a variant, a slightly more complicated variant of the usual replicator dynamics, which we know from the pure strategy case. So to say this again, here on the left you have a simplex with capital N corners, because capital N is a number of different types in the population. And point X gives you the composition of this population, X1, X2, etc. These are the frequencies of type 1, type 2, etc. And each type, type 1 for instance, corresponds to some mixed strategy, type 2 corresponds to some mixed strategy. So simplex here to the right-hand side, which has little n, small n corners, this corresponds to the pure strategies and describes what happens in strategy space, and this would be the population space. And for every composition of the population, you have a certain mixture of strategies. And the replicator dynamics is something that happens here. It describes the population dynamics, the frequencies of the different types, and depending on what happens here, the composition in the population is going to move around. And now I can introduce this notion of an evolutionarily stable strategy to John Maynard Smith. One says that strategy P hat is evolutionarily stable if whenever the huge majority in the population is using this strategy, the resident in this population is using this strategy P hat, then a small minority using a different strategy, for instance a strategy P, cannot invade, will be eliminated through selection. So this is the notion, the idea is that a small population occurring through mutation or so will be eliminated from the population. For instance, in the chicken game, where it turns out that the mixed strategy, which consists in escalating with a probability which is given by the Nash equilibrium, you remember maybe in this example I gave you it was to escalate with a probability of 10%, then this would be an evolutionarily stable state. Similarly, in a population, it turns out that the sex ratio, the frequency of producing males in the population, the sex ratio 1/2 would be an evolutionarily stable sex ratio, for instance, and so on. So if we try to formalize this idea that if the resident population is using strategy P hat, then invading minority using strategy P cannot grow, then we can compute the payoff matrix, the payoff expression. For instance, an individual using the mixed strategy P and meeting another individual using the mixed strategy P would have this payoff. An individual using P and meeting a resident individual using strategy P hat would have this payoff, and so on. So we can compute the payoff matrix of what happens if one uses P and P hat, and this depends on whether the co-player uses P and P hat. And what we want now to capture is the idea that if a small number of individuals are using P, then they will get eliminated through selection. Let's call this small number of the invading type, let's call this X. The replicator dynamics, if one just writes it down, yields this simple expression on the right-hand side. And what we want to say is that if X is small, if there is just a small minority trying to invade, then X should become still more smaller. It should get eliminated, which means that 0 is an attractor. If X is small but positive, then X should converge to 0. And 0 an attractor, this means we have to, well, this is a positive term, X, 1 minus X is positive. We have to look at the sign of this square bracket and ask when is this right hand, this is the sign of this square bracket, when is it negative? Because for small x. And what one sees immediately, that this happens for two situations. Either this expression here you see it is multiplied by 1 minus x, and 1 minus x is almost 1. Either this expression here is negative, or else, if it is equal to 0, then this expression here, which is small because it is multiplied only by a small x, should be negative. This means an ESS has to satisfy two conditions. The first condition, that P against P hat does not better than P hat against itself. Means just that P hat is a best reply to itself, meaning P hat is a Nash equilibrium. And on top of this, one should ask that if there is equality here, if P is an alternative best reply to P hat, in that case, this inequality should hold, meaning that against this invader who is using the strategy P, the former strategy, the resident strategy P hat, does strictly better than the invading strategy P. If one has this, one has the guarantee that the minority will be eliminated through the dynamics. There is a simple alternative definition of the evolutionarily stable strategy. It holds if P against P is, so the payoff for P against P is less than the payoff for P hat against P whenever P is close to P hat. And what one can show, this has been known for a long time, is that whenever you have an evolutionarily stable strategy, then it will be an attractor for the corresponding replicator dynamics. But the converse is not true. There are examples where you have, for instance, this mixed strategy M here, which is not an evolutionarily stable state, but it is an attractor. It attracts all the states which are close by. So the converse of this statement is not valid, but there is a statement due to Kressman which is valid and which is, to my mind, the best validation of this concept of evolutionarily stable strategy. It says that a mixed strategy P hat is evolutionarily stable if and only if it is strongly stable in the following sense. Suppose that P hat is in the convex hull, which is spanned by P1, etc., to Pn. So P1, P2, P3, P4, for instance, would be these types in the population corresponding to mixed strategies. And suppose that a certain mixture of these types can realize this P hat. P hat is in the convex hull spanned by P1 to Pn. This means that a mixture in the composition can realize this strategy, actually. In that case, one has the following thing. Whenever you have a state in the population such that the corresponding strategy mixture is close to P hat, then with time, this strategy mixture will actually converge to P hat. So this is a very satisfying characterization of this notion of evolutionarily stable strategy. I want to say a few more words about a completely different but interestingly related type of dynamics, which is called adaptive dynamics. I will be relatively short about this because I have strong suspicions that Josef Hofbauer tomorrow is going to say more about this. But let us consider the following situation. Let us consider an animal population and let us consider a certain trait of this animal which varies continuously. Yes, so we are considering a certain trait. This x is no longer a frequency. It is a certain trait value. And let us consider a trait which varies continuously in some interval, say, or so. This could be like the weight in a human population. Or more interesting are traits which are related to behavior. The sex ratio could be take on any value between 0, which means produce only females, or 1, which means produce only sons. The probability to escalate a given conflict could also be anything between 0 and 1, for instance. This varies continuously. And suppose now that there is a huge resident population where all members are using the same strategy, meaning now are having the same trait. So this is a homogeneous population, and all of them have the same trait X. And the question is now, if a minority is introduced by mutation, for instance, or by immigration, which is distinguished by a slightly different trait, Y. Y is almost equal to X. It differs only by some small deviation H. Will this mutant be able to invade the population or not? You see, it is the same question as before with this evolutionarily stable strategy setup. So one can compute the payoff that an individual using this mutant trait receives in a population where almost everyone, the resident population, the large majority, is using this strategy X. The payoff, of course, is something that in biological terms, in evolutionary games, is always translates into fitness, which means average reproductive success. And the question is now, can this mutant minority invade the population or not? For this, one has to compare the payoff for a mutant and the payoff for the resident. You see, an individual from the resident population has the strategy X, uses the strategy X, it has this trait, and it is surrounded by individuals, the resident population, all having the strategy X. We have to compare this, and if this is positive, then the mutant does better and can invade. Actually, what one assumes in this approach to evolutionary dynamics is that when this mutant invades, it actually takes over the whole population, which is not obvious from first principles, but one assumes if this mutant can grow, it will grow to fixation in the population. And we can now say, what about the next mutant? Will there be another mutant which will drive the trait in the population still farther? Sorry about this. So suppose we have here this trait axis. We have here the population has a value X. Here comes a population, a minority first, using a slightly larger trait Y. If it can invade, we assume that it will take over, so that if we wait long enough, this X population will be removed and everyone is using strategy Y. This is now the new resident. And then the question is, will there be a still larger Z that can invade and so on? So we assume that mutations occur very rarely, and if they occur, there are only two possibilities for them. Either they get eliminated, then we forget about them, or else they can invade, and then they will actually take over the whole population before the next mutant occurs. So we assume that mutations occur very rarely in this sense. And this yields a trait substitution sequence. I have described it here in R1. We can just as well imagine some multi-dimensional trait. And this can be described by a differential equation again, which is given by this expression, x dot, the rate of change of this trait, or the direction towards this trait of this vector field, is given, points towards a favorable direction. So in this situation, for instance, larger and larger trait values can invade and take over. There could be some other region where smaller and smaller trait values can invade and take over. So this gives a new dynamics. It is called the adaptive dynamics, and it points towards a favorable direction for selection. I mean, mutants in this direction can invade and take over. Mutants in the other direction cannot invade and will immediately be eliminated. And this has some quite interesting, this yields to some quite interesting phenomena. First of all, we can again describe what evolutionary stability means. A fixed point, x hat, of this adaptive dynamics is said to be evolutionarily stable, or more precisely, said to be locally evolutionarily stable, if this inequality here holds, meaning that for every h which is small, different from 0 but small, the payoff will be, any deviation will yield a smaller payoff. So if one is in this state, if everyone in the population is using this trait value, x hat, then there will be no possibility for deviating. Slightly smaller or slightly larger mutants will not be able to invade the population. If you are there, you stay there. This is what evolutionarily stable strategy means. Another concept, which is related but not the same, is convergence stable. It means essentially that the payoff is given by this expression, or has the same sign. The payoff deviation has the same sign as this expression. And what does this mean? Here is x hat, say. And this means that if the population is at a smaller value than x hat, then it will, larger trait values will be able to invade. So if you are here, then the selection goes in this direction towards x hat. And if you are here, selection goes in this direction towards x hat. So in this case, convergence stability means that selection leads towards this value. And the interesting thing is that these two notions are not the same. In spite of the fact that many authors used to think this, Eschel and Novak and others have shown some years ago that whereas in simple cases, like in chicken or for the sex ratio or so, you have a convergence to the evolutionarily stable strategy, it can happen that there are evolutionarily stable strategies which are unattainable, where the evolution does not lead towards them. This means that there can be situations, there can be an unattainable situation in the following sense. If the population, by chance, happens to be at this trait value exactly, then no deviation will be possible. But if it is close by, then it could be that there is no deviation possible in this direction and only deviation away from it. Similarly, if you have a slightly smaller value, that only mutants with still slower value can introduce. So this means that even if you have an evolutionarily stable strategy, it is not guaranteed at all that the dynamics will lead towards this state. So dynamics could lead away from it. So if you are simply studying evolutionarily stable strategies, you can miss what is actually happening, because you will assume, it could very well be that selection will never lead toward this evolutionarily stable strategy, even if you start close by. So far, I have not talked about population genetics at all. I have said that strategies can be transmitted by imitation, for instance, or they can be transmitted by inheritance, but so far we have assumed clonal inheritance, so to speak, that like begets like, that the offspring of an individual use the strategy of this individual. This is what is behind the biological interpretation of the replicator dynamics. But of course, more interesting animals are usually belong to Mendelian populations. And what happens then? Suppose in the simplest case that there is only one genetic locus which is describing the trait, and that there are n different possibilities, n different genes that could be at such a locus. So an individual inherits one gene from its mother and one gene from the father, one allele from the mother and one allele from the father at this locus. And we consider a gene pool, so in the population, the frequencies of these alleles are given by x1 to xn. In classical population genetics, Michael Turelli will excuse me if I skip over some details and small problems here, but in classical population genetics, the first thing is to assume that an individual having this genotype, AI, AG, these two genes, has a certain, say, survival probability, WIG, which is incidentally the same survival probability than if it had inherited the other gene. I mean, this is the assumption that AI is inherited from the mother and AG from the father. It would be just the same genotype if it had inherited AI from the father and AG from the mother. So this WIG is the same as WGI. And in that case, with some extra assumptions, one arrives at the classical selection equation to Haldane, which is many decades old, and which is just the replicator dynamics again, as you will notice. Only that the matrix W now is a matrix which is symmetric. What it describes essentially is a game where the two partners have the same interest. So a symmetric game, a game with a symmetric payoff matrix, is called a partnership game. So to speak, the father and the mother have the same interest in the child in general. So if two players have the same interest, they are certainly forced to cooperate as much as possible. And this intuitively, this means that the fitness should be maximal. And in fact, what one finds here for Haldane's selection equation is that the average fitness in the population will always be increasing, converge to some maximum. So this is a replicator equation, the classical selection equation, which describes the frequencies of genes in a gene pool. But this is under the assumption that the survival probability of an individual with this genotype is some constant, WIG, and does not depend on what the other individuals are doing. If we consider frequency-dependent population genetics, then the fitness of a genotype depends on the other genotypes in the population. So like the frequency of a genotype saying you should escalate a conflict depends on how many others in the population are ready to escalate a conflict. So in that case, we must assume that an individual having this genotype AIEG uses a certain mixed strategy again in a game. And we can compute, again, for this composition of the gene pool, for this X1 to Xn, this describes the composition X in the gene pool, we can compute the mean payoff, we can compute the mean strategy in this population, which is given by this expression here. And we can also say an allele AI uses, we can say this in a metaphorical sense, an allele uses a certain strategy, PI, because with a probability xj, this allele AI will be in a body where the other allele is of type AG. So the other allele will be of type AG. And in that case, this individual will use this mixed strategy PIG. And here we can again compute the replicator dynamics. We can say what is the rate of growth of the frequency of the allele AI in the population. And this replicator dynamics, if we write it down, looks just like a normal replicator equation, except that now the terms PI and AP and so are not linear in X, but more complex functions, polynomials of third degree. So to resume again, we have here to the right a simplex which describes the frequencies of certain strategies for a game, like for instance a hawk-dove game or so on. And to the left, we have a simplex which describes the frequencies of the alleles in a population. So this is a gene pool, and this is a strategy space. And whenever you have a certain composition X in the gene pool, this gives you a certain composition in the population, and hence an average strategy P. And one can easily see that whenever you have a rest point in this population simplex, a rest point for the replicator equation, this would correspond to a rest point for the strategy in the strategy space too. For any given mixed strategy P hat, we can look whether it is feasible in the sense of asking, is there any composition in the population such that the resulting average strategy is given by p hat. It could be that no conceivable composition in the population could yield this mixed strategy. But we say it is feasible if this set, which is usually the intersection of a quartic with a simplex, if this set is non-empty. And what one can show, but this is a fairly complicated proof. It uses a lot of central manifold theory and so on. What Kressmann, Hofbauer, and Heinz were able to show is that if there are at most, if one considers the case of at most 3 pure strategies, and if p hat is an evolutionarily stable strategy which is feasible, which can be realized by the composition in the population, then it is strategically stable in the following sense. This is now what I'm going to describe is a kind of stability condition. First of all, there exists a rest point x hat, such a rest point of the replicator dynamics, which such that if the population is in this rest point, then the mixture in in strategy space corresponds to p hat. And if you give a certain neighborhood of x hat, then there exists a possibly smaller neighborhood v, such that if you start initially in v, you remain in this neighborhood u. So this line just says that x hat is stable in the sense of Lyapunov. But x hat need not be necessarily locally asymptotically stable or an attractor. It is not so that necessarily x of t, if you start close by, converges to x hat. But what you have is that if you start close by, then the strategy mixture of the population will converge to this strategy mixture p hat. So this is a notion of stability, strategically stable, which is between Lyapunov stable and locally asymptotically stable. And Kressmann have shown that an ESS is strategically stable for if n is less or equal than 3. But it seems, correct me if I'm wrong, that now these proof techniques are close to their limit. It seems very difficult to get to some more general result about this. So in general, the interaction between Mendelian population genetics and this strategic approach is a difficult and a hairy question, especially if one introduces recombination, for instance, and more complex genetic gadgetry. To come to my last point, we have seen that there are many different dynamics, not just the replicator dynamics, but many different dynamics which can describe potentially how strategies are transmitted within a population. They can be transmitted by imitation. They can grow in frequency because rational players are thinking what they should do best. This is the best reply dynamics. They can be transmitted through Mendelian inheritance, or they can be transmitted by this adaptive dynamics setup where we assume that occasionally mutants occur and come to fixation if they yield a better result than the resident population has obtained, and so on. So there is a huge amount of different transmission mechanisms leading to different dynamics. And so far I have only considered the continuous case. I have not spoken about cellular automata. I have not spoken about discrete dynamics. I have not spoken about finite populations and so on. All this would yield other stochastic processes or dynamics, which would be interesting. But one could, of course, say, well, what are you worrying about all these different dynamics? After all, we have the concept of equilibrium, the Nash equilibrium, and isn't that already enough to solve, in some sense, the game, to understand the game? And what I want now to show is that the answer is no, that any equilibrium approach is insufficient for certain games. It must always be complemented by some dynamic approach. And I mean this in the following sense. Consider a class of adjustment dynamics. Adjustment dynamics are those dynamics in the space of frequencies of strategies which satisfies the following condition. This condition means that if the population is in the state x of t, sometime t, then some population that adapts by responding to this state of the population, some population that adapts, sorry, this has gone to extinction, some population that adapts in the sense of moving to this state x of t plus h is better off than a population that does not adapt, that remains frozen in that state. So this is, I think, the minimal assumption that one should impose upon any notion of adaptation or improvement or adjustment in a game. And indeed, so yes, this is just another way of writing down this property for the adjustment dynamics. It is also sometimes called the myopic adjustment dynamics, and it leads to this to this acronym. So if you have this property, and many dynamics have it, for instance, the replicator dynamics has this property. All payoff monotonic dynamics have this property. The best reply dynamics has this property. The adaptive dynamics has this property. So this is really a minimal assumption about the dynamics of a game. If you have this property, then, well, first of all, one can show a few things which are valid for all dynamics in this case. For instance, that whenever you have a strict Nash equilibrium, then this would be an attractor for this adjustment dynamics. One can also show that if one has a game with a unique Nash equilibrium, then there always exists a suitable adjustment dynamics such that all orbits will converge to this Nash equilibrium. So this is a statement that tends to say, okay, so it would be enough to study Nash equilibria. Only what one can show is the following thing. These adjustment dynamics, in order to have this property, must be tailor-made for this particular game. If you have one class of adjustment dynamics and try to use it in other games, then in general, it will have some limitations and will lead to sometimes not to the Nash equilibrium. What I'm trying to say is the following result of Joseph Hofbauer, that no adjustment dynamics converges to a Nash equilibrium for all games. At least no adjustment dynamics which depends continuously on the payoff matrix. There are always games, for a given adjustment dynamics, there will always be games so that the adjustment dynamics will not converge to this Nash equilibrium, but to some other attractor. And there is ingenious proof, and this is the last slide actually that I want to show. One considers a 4x4 game. And let's first assume that epsilon is 0. In that case, you see one has a partnership game because the resulting matrix, which consists only of zeros and minus ones, is a symmetric matrix. And if one has a partnership game for adjustment dynamics, then this average payoff, which is given by this simple expression here, is a Lyapunov function. It will always increase. This function, this average payoff, has a minimal value at the point f24 and at the point f13. The minimal value is minus 1/2. And it has a maximal value at this sequence of edges. Gamma is the edge from 1 to 2, the edge from 2 to 3, the edge from 3 to 4, and the edge from 4 to 1. And there also exists a unique Nash equilibrium here in the center of, sorry, it is not unique, here in the center of this simplex. For epsilon is equals to 0, this gamma, this set of edges, consists of fixed point, and this also consists, all these fixed points are Nash equilibria. But as soon as you assume an epsilon which is larger than 0, then this gamma, this set gamma, will become a heteroclinic cycle. This means along this edge, one flows from 1 to 2, then from 2 to 3, from 3 to 4, and from 4 to 1. So this is a heteroclinic cycle. And, but if the epsilon is small enough, then this average frequency, this average payoff will still increase for the corresponding adjustment dynamics that one is studying. And in that case, this means that for an open set of initial conditions in the interior of this simplex, one will converge to a set which is an open neighborhood of this heteroclinic cycle. Need not converge to the heteroclinic cycle, but to something which is in the neighborhood of this heteroclinic cycle and which is certainly away from this point P. So this means that an open set of initial conditions will lead away from P and not towards P. So on principle, an approach which is static, which does not consider the game dynamics, would be unable to describe what is happening here, because this unique Nash equilibrium P is not going to be reached by these dynamics. So dynamics are unavoidable in this sense. One has to study them if one wants to understand games completely. And an equilibrium approach will always come up against certain games where it simply does not describe what is happening. Okay, thank you very much.
Thank you very much, Karl. We have time for a few questions. Michael.
Karl, if you apply the result of Crespin, Hoffbauer, and Hines to the rock, scissor, paper game associated with those lizards that you talked about in your lecture a couple of days ago, you get a different result, or does it?
I never did this, and I must confess I'm not completely clear about this, the inheritance among these lizards, because you see these are morphs in the male lizards, and I don't know where is locus describing this. Is this on a how does one say, heterogametic locus, or?
Just to apply it formally to see if just having some genetics in makes any difference.
I agree with that. Yes, that would be interesting. One would have first to find where this gene is actually sitting, in which type of chromosome.
In general, people say that the concept of dynamics in biology substituted in a certain sense the concept of rationality in economics. But as long as we have some Nash equilibrium that are not attractors, does it mean that rational players would attain this Nash equilibrium only if they are 100% rational, but if they are 99% rational, it will be something completely different?
I think this depends very much of the game that you are considering. I mean, the problem in most situations is that there are too many Nash equilibria around. It is very rare that you have a unique Nash equilibrium in the game. In this example, there is one, but in general, there are so many. And then, even for rational players, it is not clear at all in general, except in some particularly simple situations, to which equilibriums are converging. And the same thing happens, incidentally, also for the dynamics. It is not clear which of these many equilibria will get chosen. This depends very much on your assumptions.
Please.
In the first part of your talk, you showed that for a certain number of mixed strategies, that you can use the replicated dynamics. How about a continuum of mixed strategies?
Yes. It is relatively easy to write down a replicator dynamics with a continuum of strategies. This has been done by quite a few authors. I mean, I think that Christopher Zeman was one of them, actually, Aikin, Bomse, and so on. But then usually one gets to extremely difficult technical problems, and whenever one wants to study a concrete model, one makes the assumption that there are only finitely many of these strategies in the population.
Questions? Well, if there are no further questions, let's thank Karl again.
Thank you.
So we resume 1:30. Very good.
Thank you.